As part of our problem-solving process, we need to know all the initial and final conditions of all of the components in our circuit. This includes all the voltages and currents through both the capacitors and the inductors. Now, from our DC assumptions, we know that in a DC situation, our capacitor is an open circuit, so it has no current, and we know that our inductor becomes a short circuit, so it has no voltage across it. So in the DC situation, these are both zero, so at time before zero, and after a long time at time infinity, they are also zero as well. We have another piece of information to help us. We know that the voltage across the capacitor cannot change instantaneously. So whatever value we find here at time before zero will still be the same value at time after zero. In a similar way, we can look at the current through the inductor and know that the current that's flowing through it right before time zero will be the same current that's flowing through it right after time zero. And these two pieces of information help us solve for the largest unknowns in the problem, which are the currents in the capacitor right after time zero and the voltages through the inductor right after time zero. Because these quantities can change instantaneously, we're going to have to solve for these objects. And so in the preceding slide, when we talked about changing our inductors into current sources, what we are modeling is that this current right here does not go away, and so it will influence both of these values here. And in the same way, the voltage across our capacitor will not go away, and it will influence both of these quantities as well. So we're going to need to solve the circuit 3 times for our initial conditions, looking at initial and final conditions, looking at it at time before zero, then finding out what our new voltages and currents will be, solving it at time just after zero, and then as we are used to doing at time infinity.